Hi, everybody. Welcome to the Link Lab. I'm Nicola Bezzo.
And I'm Madhur Behl.
I would like to kick off this presentation by showing you actually an example actually how autonomous systems can be used to do something very interesting nowadays. So without further ado, please meet the Jackal. The Jackal is an autonomous vehicle, so like a Google car. It contains the same sensor that you find on an autonomous vehicle, like a Google car. And here, meet the Hummingbird. The Hummingbird is an autonomous aerial vehicle, so it's a similar feature of the ground vehicles, just it can fly. So now, for 1 second, try to pretend or think that, or imagine that this ground vehicle is like a limousine, like a presidential limousine, or an ambulance, or a truck loaded with money. What we can have is that we can deploy the autonomous aerial vehicles to be the eyes from the sky for the ground vehicle. So what's happening here is that the ground vehicle is being piloted by one of my students, and the aerial vehicle actually is fully autonomous. And what is provided is autonomous tracking, monitoring, is able to provide really eyes from the sky for these vehicles. Until the vehicle is able to reach its final destination, that can be the White House for the president, or it could be the hospital for an ambulance, or like a bank if you have like a car that has a lot of money. What happens is that until it's out, the aerial vehicle can provide the perimeter tracking, and as soon as it's come back, then the aerial vehicle is able to start to track again autonomously. So it's able to provide this assurance and be able to protect the vehicles. So this is one of the examples that we have here in which we see how autonomous systems really can be used. On my shoulders here, you can see another example of this heterogeneous robotic system coordination. Here, actually, I'm showing a coordination between two completely different vehicles, completely autonomous. And this actually is one of the examples in which 1 + 1 is equal 3, because by putting together actually different resources, different dynamics, different sensors, actually we obtain something that is greater than the two vehicles by themselves. And with the same philosophy is how we're operating in the Link Lab. So we're putting together faculties from different departments, with different expertise, and by doing this, we are able to create something that is better than if this faculty will be moving and working independently.
Great, thanks, Nicola. So talking about moving towards our driverless future, I think many of us here would agree that with this hypothesis that anything which moves today is eventually going to just drive itself. It's going to become autonomous. And I'm not just referring to self-driving cars or aerial vehicles or delivery cars or trucks. They are all going to be able to drive with little to no intervention from human beings. And so really the question is, how do we get to this future? It's not going to happen in the blink of an eye. And that's one of the reasons why autonomous systems is a major area of research and thrust in the Link Lab, where we have faculty who are working on safety, security of systems which are self-learning, they are adaptive, and they are able to interact with humans in meaningful ways.
So here there are examples actually of some of the faculties that are involved in the Link Lab. They're doing research on automations. You're going to get the chance to meet these people. Probably already meet most of these people. But for the remaining of our presentation, actually, we're going to be talking and presenting you some examples where we think we are actually pioneers, and we're able to do a lot of really contribution related to automations.
So I'll start with self-driving cars, because that's one of the things that people think of when they think of autonomous systems today. And so if you were to come up with a recipe of what a self-driving car would look like, you would end up with the following ingredients. So a car really needs to know where it is with respect to its environment. That's like a localization and mapping problem. But then it also needs to figure out where everything else is, what is everybody up to around it doing. And that's a scene understanding. It's a much more harder challenge. And then the car has to combine all of what it has learned about this environment into a plan that it can safely follow and drive in this dynamic environment itself. So what is happening in recent years is that machine learning, in particular deep neural networks, have shown to work well for these perception problems. And we now have algorithms that can even make decisions on how the car will drive itself just by learning from previous behavior of human drivers. That is what you see in this video over here. What you are seeing is an algorithm that has figured out how to drive on its own by learning from historical human-driven data. So it's able to predict the steering angle for this car and therefore able to make sure the car stays in the center of the lane itself. But I want you to notice that this is pretty reliable, but if you look carefully, there's not much going on in terms of the traffic situations themselves. It's a pretty blank situation. There's no many cars, and it's very structured driving. And there's a reason for that. And the reason is that most of machine intelligence for dynamic autonomy today, it largely depends upon the underlying data which was used to train these algorithms. And so this poses a very major problem for self-driving cars. How do you ensure that the car will drive safely and reliably in situations that don't occur commonly in day-to-day traffic and are therefore difficult to even gather data on? And I'd like to show this example. It's an interesting case where the algorithm essentially has been fooled by what is a large sticker on the back of this vehicle with pictures of pedestrians and bicyclists. And so these rare events and these edge cases are really the problems for self-driving cars and pose the hardest safety challenges for us. But we cannot drive millions of miles to figure out all these edge cases themselves. That's the reason why they are called edge cases. So we need to develop better algorithms, and that's really the goal of the research, to be able to reason about these edge cases and convert them into situations that you can bet your lives on when you're driving these systems. So how do we do that? I'll just give you a little bit of flavor of the research itself. We are teaching cars to be able to drive at the limits of their agility and maneuverability. And the idea is not that the car should drive and weave through traffic all the time, but really that when it encounters a safety critical situation or one of these edge cases, the autonomous driver should have the ability to brake aggressively or turn aggressively and help you navigate that situation in a reliable manner. So how do we train our cars to have this agile controller? Well, we take inspiration from one of the best drivers in the world, or a lot of best drivers in the world. We use inspiration from Formula One and motorsport racing, where there is a saying that if everything seems under control, then you're not going fast enough. And that is really the key for what drives this research, because we train these cars to be agile by racing them against each other in an autonomous fashion. And racing very naturally presents situations where you would encounter these edge cases more often than you would in day-to-day traffic. So the way we do it is we would love to drive cars and race them on freeways, but that's not a practical solution. So we use the next best thing, which is we rely on very highly photorealistic simulation setups to train these cars. So on the left, you see a frame from the simulation or the gaming engine, which is a Formula One game. And on the right, you see the same frame from real F1 footage, and you can barely tell them apart. In fact, here's some footage from the game itself. So you can see how photorealistic the environment is. As the car makes this long left turn, you will see it will get some glare from the sun, which is how even regular cameras would operate in day-to-day situations. And what we can do is we can decompose this complex scenario into its minimal form. We can track where the lanes are. We can track where every vehicle in this scene is. We also get information on what our car is doing in terms of steering. And then we can map the position of every other agent with respect to our own car. And then we really want to boil this down into its most canonical form. And we reduce the complex situation into a graph, and the way this graph changes from frame to frame is what the deep learning algorithm is learning, and that is what I constitute as learning driver behavior. So just to show you a quick example of how this would work, here is some footage of a very regular overtaking maneuver that F1 drivers perform. Here's the driver trying to overtake very close proximity to another car. So our algorithm can learn this driver behavior and apply them to our test beds where this car has now been trained to overtake another car with the same way like an F1 driver would do today.
Beside agility, there are other problems that we need to consider if you want to enable and make autonomous systems. One of these problems is that these systems, one day, they're going to be working and living in a real world. And this real world has several issues. There are disturbance, there are noise, and there are millions of other unpredictable things that can happen. Not only that, one thing we need to consider is that besides planning and control, the system needs to be able to adapt. We need to be able to consider new paths to take. We need to consider changing velocity, changing the way they see the world. And therefore, the system needs to be able to change the way it operates, be able to learn and adapt as it's moving through the environment. Here I'm showing actually with this pictorial representation, I'm motivating this case in which an aerial vehicle may find it's more attractive to navigate to this goal, but because there is disturbance, it may be actually more convenient to stop and decide to change and go to another goal. As I'm also demonstrating here, in which this aerial vehicle is moving autonomously and is deciding online what is the best path to take, which one is the best goal to visit, when this fan speed change and the vehicle is not able to, it doesn't know a priori before moving what is the speed of a fan. So this is an example of one of the algorithms that we develop in which the vehicle is able to adapt, change, and decide what is the best path to take. Here is another example. If you're in the middle of nowhere, you don't need to check your sensor very often. If you're flying in the middle of a desert, you can actually keep your eyes closed for a little bit. While if you're in a cluttered environment like this one, you may have to actually check your sensor more often. So I'm showing actually an example of one of the algorithms that we develop in my group, in which the aerial vehicle actually is deciding at each time what is the best, when is the best time to check for a sensor and when is the best time to replan the operation. So if you pay attention to this video on the top, you see that these pink quadrators is exactly the time in which the air vehicle decides to open its eyes and to replan the operations. Okay, so far I've been showing you some examples about some of the applications that we can some applications, some actually objective and problem that we care about research. Now I would like to open a parenthesis and talk to you about some of the problems and some of the applications which these aerial vehicles and ground vehicles can be applied in a real world type of scenario. Mapping is one of these cases. So here you see actually a screenshot about what a robot sees, how the robot sees the world thanks to LiDAR and other type of sensors. So thanks to this sensor, the vehicle is able to localize itself, is able to move autonomously, and we're able to have autonomous cars like a Google cars. But these sensors enable another level actually of properties, another level of tasks that we can do. Here I'm showing actually some of these problems. We can do inspection, we can enable search and rescue mission, like what happened in Fukushima, in which were like multiple vehicles were deployed to assess the condition of a power plant. And of course, we can deploy this vehicle to do actually inspection before something could happen. Like we did recently, in which we deploy actually a series of, we deploy actually one of our ground vehicles, so it's actually the one that you see here in front, to perform actually mapping of an historic tunnel. It's called the Blue Ridge Tunnel. It's about a mile long. It was built around 1850. Right now it's closed because it's a little bit dangerous to get in. Here you see actually some images of when it was built, and here is how it looks like right now. And what you see around actually on the right is actually how it is inside. So it's pitch dark, you cannot see anything. There are rocks, there are very imprecise terrain surfaces. There are rocks falling from the ceiling, there is water also dripping. So it makes actually a very good test bed for a vehicle to be deployed without human beings. And one of the reasons we're doing this is because Virginia DOT, the Department of Transportation in Virginia, want to restore this tunnel and want to make it accessible to people. So we need to be able to assess the condition of this tunnel. So here I'm showing actually some of the results that you obtain after deploying our vehicle inside this tunnel. So what you see here is that the vehicle actually is building online the map of this tunnel as it's navigating. So here actually is moving autonomously while it's building this map. So thanks to this data, we are able to characterize this tunnel. We're able to assess what are the conditions. We're able to see if it changes over time and what is needed to do if we want to restore this place. Of course, this doesn't come without problems. One of the major issues that we need to deal nowadays is security. So here in this slide, actually, I'm showing you and pulling some of the news that you can find online that depict and show how recently hackers were able actually to compromise autonomous systems, aerial vehicle, power plants, simply by spoofing some of the sensors on board the vehicles. One of my favorite actually figures is what you see here, which actually the car think that it's going 140 miles per hour, while actually it's parked, it's not moving. And what you see here actually is a clip that is taken from a recent 60 Minutes video related to one of my DARPA projects. Actually, what you're seeing is that a hacker is able to compromise the brakes of his car, and therefore the reporter is not able to brake in front of his safety cone and end up actually hitting this pole. So how we solve this problem? So there is a need for resiliency. We need to be able to assess the condition of the systems when it's compromised, be able actually to repair the system as it's navigating. So let me give you an example. We all know, and we'll know about cruise control. If you if you want to maintain a certain speed, the cruise control is able actually to speed up if it's going slower, or if you're going too fast, it's going to slow down to be able to maintain the desired speed. So what we did, actually, we developed actually techniques that are able actually to assess the condition of a system. So by comparing what you're expecting from the systems and what actually you're getting from the system, we're able to assess if the system is actually compromised or not. So we use redundancy in sensor measurement, and with this comparison, we are able to make sure that the vehicle is always safe. So what's happening is that this vehicle is in cruise control. At a certain time, we are going to compromise some of its sensor, but because we have actually this resiliency activated, the vehicle is able to continue to perform cruise control as if actually the vehicle was never being compromised. Of course, there are a lot of problems with which we need to deal. Okay? So we can offer some solution, but the problem still exists, and probably we are never going to be able to actually completely solve this problem. What I want actually to focus here is that there is actually a lot of problem related to human factors. So what you see here actually is an image taken from a base in New Mexico in which two pilots are controlling a drone remotely. So the only interface that they have with the drone are actually these screens that you see here. If an attack happens, then the problem appears that what this operator should do. So they're not prepared to deal with this. So there is a lot of different factors we need to consider so that we can deal with cybersecurity and we can make sure that actually the operator is able to deal and take the right decision.
So talking about human factors, even a self-driving car not only has to communicate to other pedestrians and other drivers what it has to do, it needs to do a better job of communicating to its own passengers and understanding their interaction with the car itself. So everybody has a different perception of what this car behaves like. And here's an example that I really like. So this car actually expects you to hold on to the steering wheel once every 2 minutes just to make sure you haven't dozed off. And this person figured out a way to fool that system into thinking that he's holding on to the steering wheel by shoving an orange and applying pressure, all while going at 86 miles an hour and overtaking this large 18-wheeler truck. So clearly, this is an example of a person who overtrusts his autonomous system, but this level of trust varies from person to person, and we have to measure or have a way to model this variability among trust in autonomous systems amongst the drivers themselves. So here's because what really happens is that when you enter a self-driving car, all of a sudden everybody is a backseat driver. You and I have our own notions of what constitutes as safe. I have my own driving style, so has Nicola has his own driving style as well. So how do we go about in a principled way to measure trust? In our research, what we are doing is we are looking at creating a library of specific traffic situations, such as the one shown here. So when most people drive in the left lane without a shoulder and there's a wall on the left side, notice that you don't drive in the center of the lane. You will always drive towards the right-hand side of the lane itself. But an autonomous vehicle would actually drive in the middle of the lane. And many passengers feel it is too close to the left-hand side wall, and it makes them nervous. And so these are just examples of one situation that you may encounter in day-to-day traffic. Other examples are, would you trust your car to overtake this large truck on its own without even having to touch the steering wheel and without having an understanding of the momentum of such a large object? Would you trust your car to safely pass bicyclists on the road? So we can recreate those situations in simulation and have our driver drive through the same scenario and get a sense of his expectation or his notion of trust. And this data is what is going to be required to build models that can measure trust. And this is joint work that Lou and I are doing together. And so we will use these models to guide the design of the user interfaces that these cars need to happen in order to engage with their own passengers. So far you have heard about the machine learning and the systems part of it, how we make these cars safer and better. You've learned about the human side of it, but I also want to tell you that here at the Link Lab, we really like to build stuff as well. So the Link Lab is a place where we build test beds for autonomy. And one such example of a test bed is what I call F1 by 10 or Formula 1 by 10. It's a 1/10 scale representation of a real full-scale car. And we can build, drive, and race these cars to test our algorithms using the same level of perception, planning, control that you would find in full-scale vehicles. So we begin with a 110 scale car, which is a very realistic representation of an actual car itself. It has very similar dynamics, just different parameters because it's 110 the scale. We add a bunch of different sensors, the same that you would find on a full-scale vehicle today, the same kind of computation and other hardware as well. And then I make all of this available online for anybody to build this car. So you can actually go to f110.org, order all of the stuff. We even make available IKEA-style instructions for anyone to follow this build and assemble a car on its own. So you end up something like this, and later today we have a demo in the hardware lab over there. I encourage you to come check that out as well. Link Lab is also taking a leadership position in this space because for the past 3 years, I have been organizing the International F110 Autonomous Racing Competition. This year, the race is going to be in Portugal in April. And here, the idea is that all teams have the same hardware, and really the competition is about the battle of algorithms to train these agile controllers that I was talking about earlier. And so over the last 3 years, we have gone from racing in very narrow corridors to slightly wider corridors. But now, this year, we will be racing in an old museum in a palace in the center of Porto in Portugal. So if you are in Portugal or in Europe in April, I invite you to come check out this historical race. Here's some highlights from the previous F110 competition. So you can see when the car makes this turn, it'll give you a sense of how fast it is. This car can reach speeds of up to 16 to 20 miles per hour indoors, so it's really hard for us to keep up with the car if you're running with it with a laptop. Here you will see the car almost will crash into the wall but drift itself autonomously to correct itself. So it's not just about building testbeds and doing research. Link Lab is also taking a leadership role in educating the autonomous system engineers of tomorrow. Much like real racing, over here, it's also about building the correct teams. So I teach this as a course online as well. All of this material is available for people to build their own cars and learn about perception planning control. In fact, using this online course that I've taught, dozens of universities have built their own versions of F110 cars, and they share their progress with us, and they also participate in this competition. Here are the graduate students who make it happen, and here at UVA, we are doing something which is not being done anywhere else. We are teaching a course for the first time where we are going to build 10 of these cars in a semester, and at the end of the semester, there's going to be a race that you are all invited to come and watch as well. So this is just an outline of what I teach during the semester itself. And I believe there's no better way to learn about autonomy than to build cars and build robots itself. And Nicola will tell you a little bit more about that.
So before we conclude, I just want to mention that we have actually several courses in robotics and in automation, but you don't need to be like at UVA or a university to be able to learn robotics. Actually, if you have a printer, and you can print something, you can actually build your own robot at home. So we're actually building techniques toward enabling robotics to everybody, okay, even at home. So what you see here actually is an example actually of what is called origami robotics. So by printing a piece of paper, this person is able, actually one of my colleagues, is able to build actually a robot simply by folding paper. In this case actually is building actually a Segway robot, and here is building actually a ant robot. If you don't even want to fold materials, I invite you actually to look at this video here. Here actually I'm showing you an example actually of self-folding. So using lamination techniques and using like heating properties, what you can do actually, we can have actually a system that automatically fold and is able actually to create himself, you see like you see here, without having to fold material by himself. So in this case, by putting inside the oven, he's able to fold and create himself as he's doing. So here are some examples. Of course, there are 3D printers that I'm sure more and more you're getting familiar. But these are 4 examples of techniques that you can use even at home to create your own robot at any times, and this could foster more educations. Okay, so one of the things I want to say to conclude is that the Link Lab is enabling this linkage, this complicated linkage, and enabling actually us to go after really complicated type of problems.
Right, so we started with this idea that everything that moves is eventually going to become autonomous, but I want to add that it won't happen without the collaborative research that is going on here at the Link Lab.
So to conclude with this slide, I want to show you actually this is actually the map of a Link Lab built from one of my robots. I would like to mention before actually we leave is that all of this, of course, is possible because actually we have awesome students that can work on these things. So with that, I would like actually to thank my student, Hassan, Paul, and Tony, that is actually an emergency. But thanks to them, actually, we were able to do all these demos and to do the ribbon cutting and to do all of this cool type of experiment.